Well, hello and welcome YouTube. This is Mr. Robinson with yet another video. This will be a review, more of a solution guide if you will, on solving quadratic equations. The three sections we're going to be going over here though, it's not all of them. No quadratic formula, no completing the square. My next review video will probably have those things. I'm going to deal with properties of radicals. We're going to be able to simplify radicals in a lot of different ways, rationalizing the denominator, using things with variables, multiplying them, adding them, a lot of different things there. Then solving quadratic equations by graphing. Basically, how do you graph it? What does the solution look like? What are different methods of graphing there? And also even using a calculator. I actually have a graphing calculator right here. Most of you guys will have a scientific calculator. I'm not going to show the graph here. I'm just going to talk about approximating solutions with the table, the irrational solutions. And finally, solving quadratic equations using square roots. I know I have 6 problems on those ones as well. So I'm just going to jump right into it. There are 17 total problems. I hope this actually doesn't take a very long time. I may look at multiple ways to do a certain kind of problem, but I'm mostly just going to be doing the process here. And I won't be using the calculator until I really have to at that last stage right there. Okay, so the first 6 problems here, we are going to simplify all of these expressions. And what that means when there is a square root, excuse me, what that means when there is a square root is that we have to factor out any perfect squares that exist. So one of the properties involved here is this is a product first and foremost. This is 72 times p to the 7th power. So I can split up a product inside a square root into a square root into, a product of 2 square roots just like that. So I'm going to simplify the square root of 72 and I'm going to simplify the square root of p to the 7th. Now 72 has many factors in it. Perfect square factors include the numbers 4, 9, 36, and I think that's it. Those 3 perfect square values can factor out of 72. The larger the better, because if you find the largest one, that means you only have to do this step once. The square root of 72 is the square root of 36 times the square root of 2. And that is good because the square root of 36 is 6, so I get 6 root 2 simplified for the square root of 72. P to the 7th is a different story, and a lot of different ways we can go about it. Because there's only one variable problem here, I'm really just going to say the one I want to. When you take the square root of a variable, you are also raising it to the 1/2 power. So this is equivalent to p to the 7th to the 1/2 power. And of course, when you have 2 exponents here, you multiply them. P to the 7 times 1/2, which is the same as p to the 7 over 2 power. Yes, every single time that you have a square root of something raised to a power, you can divide that value by 2. Now, I don't want to divide 7 by 2, though, because that is not an integer. So what I'm going to do is I'm going to split up p to the 7th into p to the 6th times p, and they will both be in square roots. This will allow me to divide 6 by 2. The square root of p to the 6th is p to the 6 divided by 2 power. So p to the 6 divided by 2 is p cubed. The square root of p is not a perfect square, so that's going to stay inside the square root, so we'll get p cubed root p, just like that. This would be your answer if they could have these things separated like this. But as this is all multiplication, as I stated before, 6 times root 2 times p cubed times root p. What I'm going to do is reassociate some of these here. I'm going to organize the 6 and the p cubed next to each other. I'm going to organize the root 2 and the root p next to each other. And we only want one square root in the end here. All these are equals, by the way. Equals, 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 equals. 6 times p cubed is 6p cubed. How great. Root 2 times root p is root 2p. That is your final answer. And what simplification means is that the original value and the final value are the same, provided that you substitute the same value in for p. These give you the same answer. If I plugged in 2 for p, I'd get the same thing here as I would here, which is great. Okay, this next problem, the square root of 45 over 7y. And, you may sit here and wonder, okay, what is it that we can simplify? Do we just write not simplifiable? Well, I guess if it wasn't, and then I guess you would do that. But part of the simplification rules, of course, well, not of course, but is that your denominator cannot be inside a square root. And it is. It's inside a big square root right now. And I could even split this thing up, just like I could split up a product. I can split this thing up to say, hey, this is inside a square root just like that, all the same. You cannot have irrational values in the square root, so we must rationalize that denominator. So, 2 things I'm going to do. Number 1, I'm going to clean up the top. It's best to clean this up whenever you can, and the bottom if I could, but I can't. So the square root of 45 has a perfect square factor of 9. involved. The square root of 9 times the square root of 5 is the square root of 45. And the square root of 9 times the square root of 5 is 3 times the square root of 5. So I have 3 root 5 over root 7y. Okay, I took care of the top a little. Now the bottom still has kind of its issue in that there is still an irrational denominator. So what I'm going to multiply this by is the same thing on top and bottom. In this case, root 7y over root 7y. Because another great property is when you multiply two square roots by each other, well, it becomes a perfect square of that value. The square root of 7y times the square root of 7y is 7y. And on top, the root 5 gets to multiply by root 7y to get root 35y. Now, 3 divided by 7 cannot reduce. This 35 is inside a square root, so it is not actually a 35. It cannot reduce with that 7. Same with this y. It's inside a square root. It cannot reduce with that y. And 35 does not have any perfect square factors. So this is the simplified version of that problem. That is your final answer. All right, the third problem right here. We have 8 divided by root 6 plus 2. First things first, if you want to simplify a radical, go ahead and do it. The square root of 6 does not have any perfect square factors, though. It just has root 6 times root 1 and root 3 times root 2. Yes, 1's a perfect square. That is not one that diminishes this value in any sort of way, though. So what you might want to look to do is, hey, let's multiply by root 6 over root 6. But if you do that, in fact, I shouldn't be writing this in blue. I should write it in red because this is going to be wrong. If I multiply by this right here, what it's going to give me is, look, irrational numbers exist on top. That's fine. That's not what I care about. And root 6 times root 6 is 6. So what's the problem? Well, this is 2 root 6. And now this is still irrational. And no, these cannot cancel out. There is not a common multiple of root 6 on top and bottom. So there's kind of an issue at play there. I mean, you could factor out root 6 from both these terms, but then you'd be right back where you started. So that's not how you do it. No, instead, when there are two terms and one of them, at least one of them is irrational. Look, both can be irrational, but you're going to multiply by this guy's conjugate. And if this is like a plus b, we got to multiply by its a minus b. Root 6 minus 2 and root 6 minus 2 on top and bottom. What that allows you to do is allows you to FOIL these, and as this is an a plus b, a minus b scenario, it creates a difference of two squares. A plus b times a minus b is a squared minus b squared. Root 6 squared minus 2 squared. On top, I'm going to distribute the 8 into the root 6, and I'm going to distribute the 8 into the negative 2. Just like that. Root 6 squared is 6. 2 squared is 4. 8 root 6 minus 16. 6 minus 4 is 2. I'll write it over here. Is 2. So I get 8 root 6 minus 16 divided by 2. This would be your answer if this radical is simplified, which it is, and if all like terms are combined, which they are, and if the fraction was reduced, which oh no, it's not. So what do? Well, this part's kind of cumbersome. I'm just going to say it once. I'm not going to be able to deal with it in great detail here, but you need to be able, if you want to reduce this and divide 2 out, every term needs to divide by 2. Now the 6 not only is not its own term, but it's also multiplied by this 8. So if I reduce this 8 by 2, then it reduces the term by 2 already. So one way you could put it is I could factor 2 out of the top. I'll have 4 root 6 minus 8. And on the bottom, there's that 2. Now that 2 is a common multiple on top and bottom, I can divide them. They become 1, and it cancels out. And I am left with 4 root 6 minus 8. That is my final answer. So you're almost there here. I'm just cleaning this up. Both of these things divided by 2. Another way of putting it is I split up 8 root 6 over 2 minus 16 over 2, right? They're both being divided by 2. They have a common denominator. 8 over 2 is 4. 16 over 2 is 8. You can see where that comes into play. All right, the fourth problem here, 4 root 3 plus 5 root 12. The idea here basically is it's kind of like adding like terms. Combining like terms. And if you have things that end in root 3 together, then you can add them. But right now, as that's a root 3, and as that's a root 12, that's almost the same thing as saying 4x plus 5y. And frankly, there's nothing you can do with it at this point. But the difference between radicals and variables is that radicals can simplify. Square root of 3 is no perfect squares. That's still 4 root 3. But root 12, Well, root 12 is root 4 times root 3. So that makes it 2 root 3, and that is multiplying by 5. 5 times 2, as they're both rational values, is 10. And so that gives you 4 root 3 plus 10 root 3. See, now that makes it look a little bit more like these are like terms. It's like doing 4x plus 10x. And really it is. It's 4 multiples of 3 added together, and 10 multiples of 3. They're all added together, just like these x's here. 4x plus 10x is 14x. So hey, 4 root 3 plus 10 root 3 is 14 root 3. And that is cleaned up as best as I can do it. Look, even if these couldn't combine, I still simplified the expression. I cleaned this thing up into something smaller. And that's why we simplify them. It allows you to simplify. It allows you to possibly combine like terms. You have more opportunities to do things here than you did previously. All right, fifth problem right here. I have 3 root 7 plus 5 quantity squared. You know what's best for these problems is to always just expand this thing out. 3 root 7 plus 5 times 3 root 7 plus 5. Now, if I could simplify these root 7s, really I would. What I'm going to do is I'm just going to go and FOIL this thing, multiply this thing out. Just make sure you know how these things multiply. The rational values multiply with rationals, irrationals with irrationals. So 3 root 7 is going to multiply by 3 root 7. So hopefully you'll see how that thing pans out. 3 root 7 is going to multiply by 5. 5 is going to multiply by 3 root 7. And 5 is going to multiply by 5. I know I'm running out of room. That's okay. I'll move it on over. Okay, so what does that give us? Well, 3 root 7 times 3 root 7. I'm going to do 3 times 3 because these are both rational values. That's 9. Root 7 times root 7 is actually 7. So I get 9 times 7 there. Kind of nice. This 3 is going to multiply with a 5 because they're both rational values. 3 times 5 is 15. So that gives me 15 root 7. This is the same thing. 5 times 3, I get 15 root 7 there again. It's the same thing added twice. You hopefully recognize this was a perfect square trinomial, so I can show you a different way to write it if you'd like to. And 5 times 5 is 25. Well, for me to clean this up for one more step here, 9 times 7 is 63. 63 plus 25 is 88. So that becomes 88. These are like terms. Heck, they're the same thing written twice. 15 root 7 plus 15 root 7 is 30 root 7. Remember, it's still 30 multiples of 7 added together there. That's your final result. I could have written this out as a perfect square trinomial where I square this term like 3 root 7 quantity squared. I double the product of both terms here, 5 times 3 root 7, and I square the last term like that. 3 squared is 9, root 7 squared is 7, 9 times 7 is 63. You see where you add that with 25 again. And I double, 2 times 5 is 10, times 3 is 30. You get 30 root 7. So whichever way you do, it's kind of your call. Okay, this last problem right here, let me separate these along the way. I have root 6 times root 18 plus root 8. Let me show you how I'm going to start this problem, and I'm not going to continue it this way. But you could distribute immediately. You really could. And root 6 times root 18 would give you root 108. And root 6 times root 8 is root 48. You wouldn't be done, though, because you'd have to simplify these things. Now, would I rather simplify larger radicals or smaller radicals? Well, I'm going to go with the latter. I would rather simplify smaller radicals. Not that this is impossible. I already see what they are, actually. I've done these for a long time. But I'd rather simplify them and make them smaller, especially if, like with this problem right here, root 6 can't simplify, but root 18 can. Root 9 times root 2, that makes it 3 root 2. Root 8 is root 4 times root 2, that makes it 2 root 2. Look what's very nice about this problem. 3 root 2 plus 2 root 2, those two can combine, so I don't even have to FOIL. I can combine like terms right here. I get 5 root 2, and root 6 is multiplying with 5 root 2. Now, there are options on how you want to do this last part here, and I know I've said one of these things before, so I'm going to do kind of the normaler way first, which is straight multiply. Root 6 multiplies by root 2, you get root 12. Well, we've seen a root 12 before clean up, like this one here. Root 12 is 2 root 3. And 5 times 2, look, it's 5 root 12. 5 times 2 root 3 is 10 root 3. So there's your answer. You do have to clean that thing up, and that's what you get. So that is the final result of this problem. Okay, another way that you can do this, though, is this is kind of dealing with the prime factorization idea. Because I have a root 2 inside here, and because root 6 can have a root 2 factor out, I could change root 6 into root 3 times root 2. And notice how this is multiplying by 5, which is multiplying by root 2. What this allows me to do is join up my root 2's together. Root 2 times root 2 is 2. And those can multiply with the 5 right there. So I have a root 3 multiplying with a 2, multiplying with a 5. 2 times 5 is 10, and that's multiplied by root 3. So you see how you get 10 root 3 there as well. So even though I didn't have a perfect square factorization of root 6, I had a matching factorization with this root 2 that could then combine to become that. Totally your call on how you want to do that, a lot of different ways, but ultimately this cleans up into something a lot better than what it originally was. And by the way, if I did that root 108 plus root 48, it would have gotten the same answer. Okay, let's jump into some graphing here, and I have 3 different methods that I'm going to be doing here. Solve the equation by graphing. First of all, these equations are completely solvable, assuming they're solvable. They're completely solvable by other means. I could solve by factoring, completing the square quadratic formula, something I'm not going to go over here in this thing. But there are other ways to solve this thing, but by graphing, there's 3 different methods I'm going to do. Technically 2 different methods. One method is to set everything on one side of the equation like this, set it equal to 0. And when you set something equal to 0 and solve for x, that means you're finding the x-intercepts. Basically, I turn this thing into a y. I'm going to be graphing y equals x squared minus 9x plus 18. I'm going to draw this graph, but I'm going to find out when this expression is set equal to 0, so I'm going to find the x-intercepts. So on this problem here, where I'm going to use what's called the 5-point method, and on this problem here, where I'm going to use a table, I'm going to literally see where my parabola, as these are quadratic, so make parabolas, where it crosses the x-axis, if at all, or if more than once. Because it can cross it 0, 1, or 2 times. And by the way, I think all of these are covered on these problems here. So I'm going to graph this thing, and I'm going to do it by using something that's called the 5-point method. And what that is really is getting 5 critical points. Your 2 x-intercepts, if they exist, and in this case they do, your 2 x-intercepts, your vertex, your 1 y-intercept, all of these will have a y-intercept, even if it's not really good on the graph, and, shoot, I have to change the looks of these graphs, and a corresponding point, a point that's going to reflect across the y-axis there. I'm going to change the scales in some of these axes, though. You'll see I'm probably going to go up by 2, 2, 4, 6, 8, stuff like that. But you'll see that after I really figure out some of my heights here. So first things I'm going to find are my 2 x-intercepts, and that kind of goes back to my original problem here. I want to set y equal to 0, and I want to solve for x. And as long as this is factorable, this can be done pretty well. I need to find out which 2 numbers multiply to 18 and add to negative 9. Well, that's going to be a negative 6 and a negative 3. Whoops. It's x minus 3. So if I write it in factored form like that, I can now solve for x using 0 product property. If x minus 6 times x minus 3 equals 0, either x minus 6 equals 0, add 6 to both sides, x equals 6, or x minus 3 equals 0, add 3 to both sides, and x equals 3. So I have 2 of my points now actually taken care of. I'll probably do the rest of this in green. X equals 3 and x equals 6 are 2 points on my graph. Now, the thing about x-intercepts that's actually kind of nice is that they are the same height. And as all parabolas are symmetrical, that means that my axis of symmetry, the line, the invisible or transparent line that I want to draw, is going to be right in between the middle of them. That's where the vertex lies on this line here. And how did I figure out this line? Well, these are 3 apart from each other. Half of that is 1.5. So there's 1.5 from here at 1, 2, 3, 4.5. X equals 4.5 is this line. My vertex is on x equals 4.5. When I do this problem here, you're going to see a different way for me to find my vertex for sure. So the x value of my vertex is 4.5. Where is the y value? Well, I'm going to take my equation and I'm going to substitute 4.5 in for x to figure out what the y value is. This is the one and only calculation I'm going to have to make in this problem. I did not start to plug in 4.5. So 4.5 squared minus 9 times 4.5 plus 18. You know, I really should be using the calculator. What I'm going to do instead is I'm going to get the fraction 9/2 squared. People are really afraid of doing these things like this. It's quite fine. I just don't want to deal with a decimal right now. I'll convert it back to a decimal later. It should be fine. 81 over 4, that's 9/2 squared. 9 times 9/2, that's minus 81/2 plus 18. If I multiply this by 2 over 2 and multiply this by 4 over 4, that's 81/4 minus 162/4 plus 72/4. Negative 162 plus 72 is negative 90, so 81/4 minus 90/4 is negative 9/4. So that's negative 2.25. So that's where my vertex is at. It's at negative 2.25. So that's going to be right here. Negative 2 1/4 right there. So there's my vertex point. And look, there's no faster way to do that outside of using the calculator. You could have done your negative b over 2a method, which I'm going to do over here, and you'd still have to get that value regardless of where it is. But I still did find it, and I'm still going to use it. Now, there's one thing that I did say about this problem that I want to do. Because I'm using the 5-point method here, I am actually going to change the scale of these because my y-intercept is the next value I'm going to get. And I'll write it right here. The y-intercept is the value of y when x equals 0. 0 squared is 0. Negative 9 times 0 is 0. 0 plus 18 is 18. My y-intercept is at 0.18. Well, I can't fit 0.18 up on this graph because these go up to 10 only. So what I'm going to do is I'm going to make these go up by 2 each. 2, 4, 6, 8, 10. 20, 40, 16, 12, 14, 16, 18, 20, like that. That means this is going down this way the same kind of way, and that means I have to change my vertex a little bit. So 2.25 is now actually, or negative 2.25 is actually probably now like that. It's a lot closer. Now it's like, it almost looks like negative 1 1/8 because it's halfway from 2 1/4, negative 2 1/4. So my y-intercept is at 0.18, which this is 12, 14, 16, 18 right there. That's going to be my y-intercept. Okay. There's that point. My final point, my corresponding point, will be reflecting across this axis of symmetry the same distance away that my y-intercept is, because these points are all about symmetry when they're at the same height. This point is 1, 2, 3, 4.5 units away from here. So 0.5, 1.5, 2.5, 3.5, 4.5 away right here. 9 over, more than half of 4.5. Or double 4.5 gives you that one there. So those are my 5 points. I could have plugged in a lot more points. I'm going to do that for my other graph. But here's my graph right here. These parabolas are not going to look good when I draw them. I do apologize for that. Or I don't plan on them looking very good. So don't base everything off my thing here. It's very hard to get it kind of taken care of. Really, I should iron this out and get some more points. But I'm going to take care of it just like that. All right, well, that's graphing it. And I'm going to always ask for 5 points. I think that's really important for a parabola. It really shows how there's a different kind of growth instead of just something linear. I don't think 3 points is enough, and I think the vertex is huge. But what they want is the solution. Clearly, I found this in the very beginning. Excuse me. These were x equals 3 and x equals 6. But the purpose is twofold. Number one, you're practicing graphing. Number two, you're trying to understand what it means to solve them. Number three, generally the 5-point method might not be a way that you can always do. So if it's not factorable, then what are you going to do when it comes to graphing, right? So there was that problem right there. I'm going to go over the next one. This time I'm going to do it just with a table. And when it comes to a table, it's the same kind of thing. I want to set this in standard form. I want to add that 4 over. Plus 4 equals 0. So essentially, I'm going to graph that equation right there. I'm going to graph y equals x squared minus 2x plus 4. I'm going to find out where they cross the x-axis, if at all, or if more than once. Okay, and then if I get 5 points graphed, I'm going to state the solution based on where they crossed if I do find a good spot. Now, first things first, 5-point method is not good for this problem because it is not factorable. There are no two numbers that multiply to 4, positive 4, and add to negative 2. So 5-point method for me is already out. That's why I'm kind of opting to just do my other way here. So I'm just going to use a table. So I'm going to do an XY table, and I like to write the expression in between, at least with you guys, to really show how to substitute things in. But the thing about parabolas, and you saw that with this problem right here, is you don't just choose some negative numbers and some positive numbers because you don't know where the vertex is. In this case, it was all the way out at 4.5. Heck, I didn't even find the vertex. I wouldn't have found the vertex with integers. I had to actually do some computations to figure it out. I'm going to do the same thing here. I'm going to figure out where the vertex is, and I'm going to build my 5 points around that vertex. So, the x value of the vertex is obtained, excuse me, by negative b over 2a. And by that, I mean if you have an equation in standard form, y equals ax squared plus bx plus c, the vertex is found by taking the opposite of the linear coefficient and dividing it by double the quadratic coefficient. And you still don't know why that is, and there's no reason for you to really understand it yet. I promise to explain it more when I talk about quadratic formula. Otherwise, your calculus teacher will also prove it to you that way, actually pretty quickly. Once you learn calculus, you'll learn that proof and go, oh, okay, I get it. So, excuse me, hang on a second. So, negative b over 2a, I'm going to substitute, remember this a value is 1 right here. I'm going to substitute the opposite of negative 2 and divide that by 2 times 1. That's 2 over 2, which is 1. So the x value of the vertex is 1. And look, that's not far away from 0. It's not far away from the middle. I couldn't risk it, though. I didn't personally know off the top of my head. I mean, I didn't. So I found out that that one was 1. That's good, and I'm going to build around that. Why not say 2 and 3 and 0 and negative 1? I'll show you some tips and tricks here with calculating these. Pretty straightforward. So I'm going to plug in 1 for x and figure out what y becomes when I do that. That'll give me my vertex point. So I'm going to do 1 squared, which is 1, minus 2 is negative 1, plus 4 is 3. 1, 3. And I'm already getting something interesting when it comes to this graph here, and I'm going to tell you what it is in just a moment. Okay, this is my vertex for this graph. This graph is a positive x squared quadratic. That means it is a right-facing up parabola. I don't know exactly what it looks like yet, but I know that it goes upward. And I know I calculated everything just fine with that 1, 3. So, if I'm trying to find where they cross the x-axis, I already know there's no solution to this thing. And if I'm taking a test on this kind of stuff, I might state that. I might go straight to, why should I keep graphing? No solution. I know it's going to go upward. You ask me to solve by graphing, there's nothing to solve. It doesn't cross the x-axis. And what that actually literally means is there's no value I can plug in for x here and get negative 4. It's impossible. It just is. You can try it, but this graph kind of proves there's no solution. That being said, I want to keep plotting points for the graph. I'll keep doing that, and we should be good. What I like about 0 for x here, just like the other one with the y-intercept, we get 0 minus 0 plus 4. That's 4. Didn't even have to compute anything to calculate that, really. As this is the vertex, and as this is 1 away from 1, this is also 1 away from 1, so this will be the same height here. If one's 4, then the other's 4. All that's left is either substituting a negative 1 or a positive 3. And you know us, we feel safer probably with positive numbers. So let's square the 3, and then let's subtract double 3, and then we'll add 4. 3 squared is 9, minus 6 is 3, plus 4 is 7. So this is 7, and that's 2 units away from the vertex. So this one up here is 7, which is also 2 units away from the vertex. And you know, I didn't have to change anything on this graph. These look like they'll come out pretty well. 0, 4, negative 1, 7, looks like that. And 2, 4, and 3, 7 looks like that. I have my 5 points. There's a better looking graph when it comes to it. It's going to keep going up like that. So yeah, you know, when it comes to this graph here, it doesn't intersect anywhere. And, you know, I did mention early on that this graph wasn't factorable. It is not true. I'm going to write no solution. It is not true that just because a graph is not factorable does not mean just because a graph is not factorable does not mean there's no solution. But if a graph has no solution, that does mean that it's not factorable. So I can tell you that much right there. This is no solution, therefore this is not factorable. But as this was not factorable, didn't mean there was no solution. There could be, and I know we are going to run into a problem that is not factorable that does have solutions on the next slide. Okay, in the last problem here, I'm going to do a 2 expressions form, and basically what that means, and literally we were doing it here, I'll explain how, but I have negative x minus 16 as an expression. I have x squared as an expression. Previously, we put everything in standard form and set it equal to 0 so we could find out where they cross the x-axis. So we set y equal to this expression. This time, I'm going to set y equal to both expressions. I'm going to set y equal to negative x minus 16, negative 8x minus 16, excuse me, and y equal to x squared. I'm going to graph these two graphs here. I'm not going to compare them to the x-axis. I'm going to compare them to each other. I'm going to find out where they intersect with each other at what x values. That's solving them. And you find out what x value makes the left side and the right side give you the same y value. Of course, as these are both set equal to y, if I plug in that certain value for x that makes both true, and there may be more than one value, or there may be one, or there may be none, then that will match with all the other ones. Now, these are two different looking graphs than what this graph was with this graph here. You might not know this, but we were also graphing y equals 0. If the whole point was to find out where this crosses the x-axis, guess what the line y equals 0 looks like? Yep, it looks like that right there. And what does y equals 0 look like over here? You betcha, this horizontal line, the x-axis. So yes, we were graphing this graph with this graph and finding out where they intersected with each other. And I'm about to do the same thing over here. Now, I didn't have to draw that because there's another name for it, and it's called the x-axis. And I don't have to find their point of intersection because those are also called x-intercepts. So I didn't have to give them that name, but that didn't change what we're doing over here. So you can graph them like this separately and find out where they intersect. Just find out what the x values are, though. It doesn't matter what the y value is in this case. Do these equations have y's with them? Nope. So yeah, the y values don't matter. It's the x values that do. So let's go and graph these. I'm going to start off with y equals x squared, and I'm going to make it blue. And y equals x squared is pretty straightforward. The vertex is at 0, 0. If you want to think about it as negative b over 2a, well, guess what? Here's your equation. Negative b over 2a, that's negative 0 over 2, which is 0. I don't even know why I kept the negative there. So the x value of the vertex is 0. And the y value, y equals x squared. Why do I even need to do a table? 0 squared is 0. There's my point. And I can do a couple more. 1 squared is 1. 2 squared is 4. Over 2 up 4. 3 squared is 9. And, you know, given this problem here, I'm actually going to have to change the scaling again because I'm seeing a y-intercept of negative 16. So bear with me for just one moment. I'm going to call this 10 again. And I'm going to call this 20 again, and that does mean that where these points are is going to change, actually. So I'm going to take these and drag them half of what they were before. If this is 2, then half of that's 1. So here's my 1, 1. And so, by the way, my x's aren't changing. That's going over 5 and such. So I probably should actually write that down, but, you know, kind of on the lazy end on this one. And actually what's good about this is I can plot another point. 4 squared is 16, and 16 is right there. So that's nice. I like more points with parabolas. It really makes my drawing work out a little better. And what's going to happen here, I'm going to square the negative numbers, and they become their positive versions. Or, of course, I'm reflecting this over. If you remember that. Those turned black. I'm sorry. I'm reflecting these points over. This is 3 away from here, so this is 3 away from here on this side. A lot of different ways you can really graph these. You know, a table is just one part of it. You can actually mix and match all these portions right here. So it'll kind of be a cool looking parabola if I can get it even close to right. I always like them when they're a little bit wider. You know, tall and skinny doesn't give me that great feature set that I like. I really like the look of wide parabolas, but of course I changed the scale here. So it's not like the parabola widened out. The window just shrunk. So there's my y equals x squared equation. Now, the fact that I have these axes is going to be kind of important for me for this problem because I need to find out where these points intersect. And really, if this is more of an Algebra 1 concept, I'm really only finding out if I'm going to overlap some of these integer dots right here. All right, y equals negative x minus 16. This is a y equals mx plus b form here. Y equals mx plus b, where m is your slope, like negative 8, and b is your y-intercept, like negative 16. And if your y-intercept is negative 16, that means when x is 0, y is negative 16. So if we go down, negative 10, negative 20, negative 16 is right here. 0, negative 16, that is a starting point for my graph right there. My slope of negative 8 means that every single time that I fall 8, I will run over 1. Now, you know, maybe I should mark these scalings here. This is 5. This is negative 5. This is 5. This is negative 5 right there. Okay. Where was I? If I fell 8, I would run 1. Now this is going to be kind of tough because it's way down there, but I might as well plot a point so I can make my point. Literally, no pun intended. And if I rise 8, I will run 1 to the left. So here, rising 8, 2, 4, 6, 8, run 1 to the left looks like that. 2, 4, 6, 8, run 1 to the left just like that. 2, 4, 6, 8, run 1 to the left just like that. 2, 4, 6, 8, run 1 to the left just like that. And keep in mind here, this point is negative 4, 16. I had a point on this graph that was the same thing. Okay, I'm going to go ahead and draw a line now from what I have. And, you know, this ends up kind of being an iffy and sore subject to talk about because my graphs are not so great. Ooh, let me change that thing. My graphs are not so great as to really convince you where it's intersecting and where it's not. So let me try and do the best that I can to explain it, and then I promise I will move on. Okay. So there's my line right there. Okay. First things first. A function is not a function if you can have multiple y values for any one x value. And the reason I'm making that case right now is because I have a point here that's negative 3, 8 for my green line. I have a point right here that's negative 3, 9 for my blue curve. These do not intersect at the same place. One is at negative 3, 8, one is at negative 3, 9. Because they're at the same height, these will never be at the same place at this x value. So they just won't. They just won't. The next thing I want to make mention of is these two do overlap at the exact same place at negative 4, 16. If they overlap at the exact same place, then that is a solution. That is a point of intersection. X equals negative 4. This line right here does feature a point of intersection of those two lines. So I want to make that perfectly clear. This is a solution. Let's see if it's the only one. The tough part with this is our graph and our drawing with this. I'm going to try and explain this part the best that I can. This slope is constant. This slope is negative 8 over 1. No matter where I go, negative 8 over 1. My blue curve is ever changing its slope. You don't ever even really call it a slope, but it's steepness. It just steepens a little bit more as you go over and over and over. But what I can do for now, for the time being, is really calculate average slope. And let me zoom in on this thing because I'm not really paying attention to those other ones right now. That's not much. This average slope from this point, which is already above the green one, by the way, to here, where they actually do meet, has an average slope of negative 7 over 1. The next time this goes up to negative 5, 25, way up there, that will have a slope of negative 9 over 1. So this thing will have steepened. It'll go up, it won't go straight up, but this will have steepened, whereas this one will keep going this way. This line, how can I grab the line? This line will keep going off this way. So there's a point prior to where the blue is above it. It lessens, its slope is less steep than the green one up until they meet together. They touch at one point, and then this one steepens up and takes off, and it will take off for the rest of the time. This is a point of tangency. This is the only point that they're going to intersect at, negative 4, 16. I know it's hard to see. I know this method isn't best if the drawing's not perfect, or if it just doesn't feel great to see whatever this and that. But I did remind you that unless they intersect at cross sections that you can clearly find, you can probably count out the fact that they're probably not intersecting. It's not like you're going to be given a graph that looks like this, where it crosses in the middle of something and in the middle of something. No, you're not going to do something like that, especially not when you're solving by graphing. But right here, this is where they cross. This is above it here. This is above it later. So this is the only time that they touch. Therefore, that's the only point of intersection. That's the best I can say. Outside of that, let's just prove it here. I'm going to solve this one by factoring. I'm going to subtract the 8x over and add the 16 over. And that factors into x minus 4 quantity squared. That's to two numbers that multiply to 16 add to negative 8, or it's a perfect square trinomial. X minus 4 quantity squared equals 0, so only 4 would make that true. X equals 4. I did something wrong here with my graph. Oh, that's a negative 8x, excuse me. So plus, minus, there we go. X equals negative 4. And that's your solution. I couldn't see that negative right there. So there you go. That's it, and that's all for that one. Those are the 3 different methods. This one is less safe when it comes to really finding the solutions, but it just goes to show you that you do get the same solutions. Even if I put these all on one side of the equation and graphed it, it'd be a different graph, but it would have the same intersecting value. So those are the 3 graphs right there. All good and dandy. 3 different forms. Have some fun with those. Okay, solve the equation by graphing. We have 2 more problems with this. This one, you're given the graph. Here's the graph, and this is a cubic function. It's not a quadratic, and they get kind of funky. A cubic function can have as many as 3 solutions, and this thing spares no intercepts when it comes to that thing. It intersects at 3 different locations, here, here, and here. And then when they ask you to find the zeros, you know, it's fun for them to give you an equation and such, but they give you the graph. These are the 3 zeros mean x-intercepts. They mean solutions to these kinds of equations here. You're trying to find out when this thing's equal to 0, what x is equal to. And of course here, x would be equal to -4. X is equal to -2 and +1. And, you know, those are the 3 x-intercepts. -4, 0, -2, 0, and 1, 0. And that's the answer. Really, that's all you have to say. If I wanted to be a little more particular with you and solve by factoring one more time, I will. So x plus 1 times x squared plus 2x minus 3 equals 0. And the whole intent, you know, you set y equal to 0. And your whole intent is to solve for x. Y can use zero product property here, but even before that, I look at a factorable quadratic in the form of x squared plus 2x minus 3. The 2 numbers that multiply to -3 and add to +2 are a +3 and a -1. Well, okay, you know what? It's a good thing that I did this scenario here because I wrote the wrong answer. Maybe I should pay more attention to what I'm doing. Okay, well, it's good that I'm doing this right now by double checking. Zero product property shows that if this plus this times this equals 0, either x plus 1 equals 0, so x equals -1, not an answer that I wrote, or x plus 3 equals 0, so x equals -3, not an answer that I wrote, or x minus 1 equals 0, so x equals 1. Hey, that's an answer that I wrote. But I clearly messed up here, probably because where I drew the red things, and maybe that's where they're trying to clear you. Oh, that looks much better. Okay. So where I drew those red things were kind of bad. Let's not do big circles. Clearly that's 1, 0. Clearly that's -1, 0. This is -2. That's a little ambiguous, but if you count, you'll see. And clearly that's -3, 0 right there. So my initial answer was wrong. It's a good thing that I double checked, and it's a good thing I guess I don't edit this video to really show you the fact that even teachers do make mistakes. Of course, that was a perceptual issue, and I really should have paid more attention and not been as carefree. But it wasn't too carefree because I did factor. I solved by factoring, and I got those answers that way. But finding the zeros with the graph is totally attainable if you know what you're doing to find them. Just find out where they cross the x-axis and make sure you know how to count. Okay, this last graphing problem here, let's graph this function. Remember, this does mean y equals. Let's approximate the zeros of f to the nearest tenth. That can probably tell you right now 2 things. Number 1, this is not factorable. Number 2, if they're asking us to approximate zeros, that means there must be some zeros, which means there are solutions. So this was the case where I said, just because something's not factorable doesn't mean it's no solution. But if something's no solution, it means it's not factorable. Is this one factorable? What 2 numbers multiply to -5 and add to +2? I thought so, right? There's nothing. So you can't solve it that way. But we are going to have to graph it. And I'm going to graph it using the table method I did before. Here's your y equals equation. I just want to write y equals. I think it's probably easier on your eyes if I do that. Let's find the vertex. For the vertex, the x value is -b over 2a. That's -2 over 2, which is -1. So the x value of the vertex is at x equals -1. We know it's somewhere along this line right here. Okay. Now, the y value is going to be found based on plugging in the x value there. So I'm going to do that in just a moment. Let me clean this stuff up here. So the y value is by plugging in that x value. And I might as well just do it in the table that I make. So, and I'm going to mostly do this, I'll just do a 2-column xy table right here. So, oh, sorry, bad table. So -1, I plug into here. -1 quantity squared is a +1. We'll get -2, that's a -1, -5, that's a -6. So -1, -6 is my vertex value. There it is. Let's plug in a 0 and a 1, and I think we may even have to plug in a 2. I think it's going to go I don't think we're quite going to get there just yet at 1. 0, pretty simply, is -5. That's the y-intercept right there. 1, we're going to get 1 plus 2, which is 3, minus 5 is -2. And 2 is 4 plus 4, that's 8, minus 5, which is 3. So cool. I have surpassed the x-axis right there. I did not get a 0 value on it, though, and that's expected, especially with the problem that you see. Based on what you have here, do I need to put in -2, -3, -4 in the table and write the reflections here, or can you reflect them this way? You can reflect them. You can graph however you need to. I'm getting my graph in a way that I know how to do, and it's going to help me out there. I could be ultra impressive and show you what the next value is, and I'm just going to say it. I think it's right up there. So, I'm just giving you the graph. 5 points is really the requisite, but you really want to pass or land on that x-axis if you can as well, because really that's a big portion of what it is we're doing. We're finding the solutions. We're finding out what the x-intercepts are. Not the best looking graph, but not bad. But given that I had points, it could have done better. It's kind of hard to do drawings on this thing, I'm telling you. Okay, so there's the graph. Approximate the zeros to the nearest tenth. So the zeros, those are the x-intercepts. Now, they cross the x-axis not at integers. We know this because we calculated this stuff. At x equals 1, there was a negative value. At x equals +2, there was a positive y value. So between 1 and 2, there's a solution. We just don't know what it is. And no, it's not necessarily just 1.5. It could be. In fact, I want to change this tenth to 100th. I want to be a little more particular here. I could do 1,000th if I really wanted to. I thought this already did say 100th. And this one here, it's somewhere between -3 and -4. Not necessarily -3.5. All right, so what we're going to do here is we're going to use the calculator at this point. Okay, so with that calculator, where is mine? With the calculator, here's what you're going to do. And I know you may have a different calculator than I do. So you have a button, if you're using a TI-30XS multi-view, there's a button kind of around here that says the word table. You would press that table button and you would be getting a y equals equation. I'm going to hit this button that says y equals. You're going to type this equation out, x squared plus 2x minus 5. I know that your x is swimming somewhere around the bottom right there. You'll see a big X there. Mine is up here. I can't tell you where your calculator is, what your calculator does too much because it's not in front of me. And me saying the words might not help very much. Okay. Now, just so you know, I can graph this one. Yay! And look, it looks beautiful. And it kind of matches mine, and it's better. But that's not what I'm going to do. I'm going to look inside the table. Now, when you hit enter after typing in your equation, then you get parameters that look pretty similar to this. You're going to be prompted to type in a starting value. You're going to be prompted to type in what's called a step, or in this case, a change in your table. A 1 means that every x value is going to jump by 1. I'll start at 0, then it'll be 1, 2, 3, 4, etc. If I put in a 4 or a 5, for example, it would say 0, 5, 10, 15, 20, etc. Keep this keep your variable, your x, your independent onto auto. If it does ask, then you're going to have to plug in your own values, and the whole point is to not guess and check, but it is to be rummaging through these things the way you're supposed to. Now, I'm going to put my table set at 5 just for a moment so you can see what I mean when I go to table. You would hit OK on your calculator, perhaps, and you can see my x values jump up by 5. And the y values give you what it computes when it plugs in these values into here. So yeah, it's another way I could have done my table here. I could have gone back to my table where I had a -1, and I went up by 1 each time, and you can see where I'm going to get those values matching what I had before. -1, -6, 0, -5, 1, -2, and 2, 3. And guess what my next point is? 3, 10. See if that one matches. 3, 10. It's up there. So, and I could have found the other values here. If you want to see that symmetry, there it is. -5, -5, -2, -2, 3, 3. Looks beautiful. Very nice symmetry across my vertex, which is right in the middle. Okay, so what am I going to do? I'm going to approximate solutions. And here I have where x equals 0. Here's where x equals 1. Here's where x equals 2. Somewhere in between where x equals 1 and x equals 2, I get a y value of 0. So I'm going to start my table at x equals 1. And I'm going to change my table increment I don't know if incrementation is a word, but I'll say one. My table incrementation to 0.1. I'm going to shift the decimal place over. If I want to go to the nearest hundredth, I'm going to start by going to the nearest tenth and just work on accuracy. Then I'll try and get some precision along the way. Somewhere between here, just like here before, it went from negative to positive. This went from negative to positive. So I want to find the two x values where my y's go from negative to positive. And it looks like it's in between 1.4 and 1.5 for x. So somewhere in between, and it's almost right exactly in between, almost, if you think about it. Somewhere in between there, to the nearest hundredth, I can find a number that's precise enough for me, or at least for us, to be able to do that. So I'm going to start at x equals 1.4 this time. 1.4. And I'm going to change my table to 0.01. And in doing so, let's see what we get. 1.4, 1.41, 1.42. What does it go from negative to positive? Well, between 1.44 and 1.45. And guess what? You can do this all day. I could go to the thousandth, 10,000th, 100,000th, millionth. This is an irrational solution. It goes on forever. You can go for 1,000,000 decimal places and you still won't get exactly 0. Your calculator will give you 0 at some point. It'll give up, but it's never exactly 0. So we're rounding it. We're approximating it as best as we can here. Now, which of these two numbers gives me a y value that's closer to 0? Well, this is 0.0025, and this is just 0.0464. It doesn't matter if it's negative or positive. This one's farther away from 0. This has 2 leading zeros after the decimal, and before the rest of the numbers, this only is 1. So 0.0025 is my closer y value, and that happens when I plug in 1.45 for x. So one of my solutions to this equation, approximately so, is x is about 1.45. To the nearest hundredth, I have determined a solution to that. This next one I'm going to do a lot faster now that you've kind of heard all that process again. This is between -3 and -4. So I'm going to go ahead and go to -4 here, and I'm going to start with a table change of 0.1, and I'm going to find when this goes from negative to positive. So it looks like between -3.5 and -3.4, it goes from negative to positive. You're going to see probably a pretty similar themed thing with this problem. I assume -3.45 is going to be the answer on this one here. Because it's all about symmetry away from -1. And if this is 2.45 away this way, this may be 2.45 away that way. That is how it works. That's kind of for the more informed for this stuff. So I'm going to start at 3.5. It's going to be between -3.5 and -3.4. So let's see. And right here, between -3.45 and -3.44, it goes from negative to positive. And again, you see that exact symmetry again. Because our vertex was at a -1, it's going to be pretty clean. So 0.0025 is closer than -0.0464, so -3.45 is closer than -3.44. So rounded to the nearest hundredth on this other side right here, x is also approximately, not exact, not even close to exact, -3.45. Those are the two solutions. You want exact solutions. There are other methods to do them that you have not learned yet, but guess what? It will be an irrational solution. It'll have a square root in its answer. That's the point. It'll have a square root in its answer. So I hope that's the end of the calculator use. I'm going to go and hide that one away, and that's graphing that problem and getting all that answer stuff there. That is the rest of 9.2. Okay, finishing off section 9.3. This will actually go pretty quickly. Maybe there's some things I want to say here and there. We're going to solve using square roots. The basic thing behind this is that if there's an x squared term, you can tell there are no linear terms, which is great. So there's an x squared term here, 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 and here. And here are quantities that involve just one x right there. It doesn't matter. There's a quantity that's protected by its square. I want to isolate my squared terms and quantities. That means I want to get them by themselves. So I'm going to subtract 5 from both sides from this first problem here. So when I do, I'm going to get x squared equals 12. This allows me, now that I'm isolated with this and no other x terms are anywhere else, I may now do the inverse of squaring, which is taking the square root of both sides. Now the square root of x squared is actually the absolute value of x. It's not just x, because this could have been a negative value, and when you square it, it becomes positive. So we need to make sure that we account for, if it's negative, we got to kind of get its positive treatment as a result. So we got to say, what could have x been if the absolute value of x was root 12, which by the way simplifies to 2 root 3 from section 9.1, then x could have either been a positive 2 root 3 or x could have been a negative 2 root 3. And those are exact answers. You know, I'm not going to round these solutions here. It's not necessary. These are exact. You're probably going to be expected to do some exact ones like this. If you want to use a calculator and round it, go ahead. But that's what I'm just going to write right there. Okay, this next problem here, x squared minus 14 equals negative 14. Same kind of idea as the last problem here. I'm going to add 14 to both sides to isolate my x. But you see here, they both cancel out. So I'm going to get x squared equals 0. So what times itself gives you 0? Well, the only possible case for here is 0. Regardless, let's treat it like square roots like before. Square root of x squared and square root of 0. The square root of x squared is the absolute value of x. The square root of 0 is 0. So x could either be a positive 0 or x could be a negative 0. Don't play that childish game stuff with me, boy. It's just a positive 0. That's your only solution. There is no such thing as negative 0. There's just one answer. This also does mean if you found a way to graph these things, they're only going to intersect at one point. This would happen to intersect at 2 points. All right, this third problem is a little different because now x is inside a quantity. Well, if you're going to solve this using square roots, let me tell you that the right away wrong method of going about this is by expanding this into x squared plus 4x plus 4. I want to note, and I'm going to write it anyway, that doesn't make this something you can't do, but they are asking you to use square roots, so we got to follow alongside that. I'll finish that up later. I'm going to go in this blue method right here by taking the square root of both sides. My quantity is isolated. My squared quantity is isolated. I can do that square root immediately. So the absolute value of x plus 2 equals square root of 64 is 8. So that means that this thing that I take the absolute value of to get 8, this thing could have been 8, or this thing could have been negative 8. Subtract 2 from both sides, you'll get x equals 6. Subtract 2 from both sides here, you'll get x equals negative 10. You can always double check these right here by plugging them in. I'm going to go ahead and double check it by using this here, but 6 plus 2 is 8, 8 squared is 64. Negative 10 plus 2 is negative 8, and negative 8 squared is 64. That's why this one is important to keep there as well. See, this problem, I could subtract that 64 over, and I'm only going to do this kind of thing once. Equals 0. The two numbers that multiply to negative 16 add to 4 are 10 and negative 6. Zero product property here. X would equal negative 10 and x would equal positive 6. So they're the same answer there, but we did the square root method right there. That's the way that's going to be enforced, and I'm going to do it again that way. Okay, 4x squared plus 25 equals negative 75. So I'm going to subtract 25 from both sides. Again, I want to isolate my quadratic dude right there. It's not fully isolated. 4 is multiplying with that. So let's divide both sides by 4. Let's go ahead and take care of that. Divide by 4. We will get x squared equals negative 25. Now, I'm going to take the square root of both sides, but right here you could pause it and ask yourself, what number could I square to get negative 25? And you can try every real number in the world and you won't get anything that pans out. But there are imaginary numbers that do work. But the square root of negative 25, you try in your calculator, it'll also say error. I'm not going to do it with mine. But you could also, without these square roots, you could also ask yourself the same question, like I was talking about. What number do you square to get negative 25? There's no real number that does that. Just like what's the square root of negative 25? There's no real number that does that. This is no solution. No real solution, at least. And, I should have been saying that for the other problem. When we graphed, I should have said no real solution. I really want to get in that habit. When you're in Algebra 2, that'll be important. You probably won't even say no real solution. You're going to find the imaginary solutions to them. And I know people sometimes chuckle when I say imaginary numbers. That is a real term. It's funny how, ironically, it's a real term. It's an actual mathematical term. Not my favorite one, but they do exist. There are numbers that you can plug in to get them. They're just not real numbers. Okay, now the other thing with this is, like, say that I graphed this. If I added that 25 over and I graphed y equals 4x squared plus 100, all that means is this would never cross the x-axis. There's no real solution, no x-intercepts. This has 2 x-intercepts, this has 1, this is 2. That's all. X minus 1 quantity squared equals 0. Cool, this squared quantity is all to itself, so let's take the square root of both sides. That gives us the absolute value of x minus 1, and the square root of 0 is 0. that means that x minus 1 could equal positive 0 or negative 0. And just like we talked about before, there's only one form of that, so that's just 0. If x minus 1 equals 0, add 1 to both sides, you get x equals 1. That is your only solution, the only thing that could work. 1 minus 1 is 0, 0 squared is 0. It's the only possible solution. And your final one right here, we have 19 equals 30 minus 5x squared. So I want to isolate my x squared term again, and I like to make it positive. It makes me feel better, and I like it on the left side. It makes me feel better. So I'm going to add 5x squared to both sides to get that on the left side and make it positive. I'm going to subtract 19 from both sides just like that there. So I get some cancellations here and here, and now I have an equation that says 5x squared equals, what is that, 11? 5x squared equals 11, so x squared, if I divide both sides by 5, x squared equals 11 over 5. Now do not write this as a decimal. We are going to deal with fractions as we have for simplifying radicals previously. And we have to do that in this form again. Take the square root of both sides, and what do we get? The absolute value of x on this side. And as you know, a square root like this does not work. This is not something that we want. We want to split this thing up, and we see that we have an irrational denominator, and we want to rationalize it. Now, I also have to split this up into two equations like this. So if the absolute value of x is this, then x could either be a positive this, root 11 over root 5, or x could be negative this. You'll see some people put like plus or minus it. Eventually, you're going to see me doing it as well, but I want to really enforce there are two separate solutions, two equations split up, really getting that. With both of these, look, it's going to be the same version, just one positive, one negative with this answer, but I got to multiply top and bottom by root 5. That's what's going to rationalize my denominator here. And root 5 times root 11 is root 55. It doesn't have any perfect square factors in it because these are prime numbers in themselves already. And that's root 55 over 5, which remember, that's not an actual 55, that's root 55, so no, these cannot reduce. Or here, x is negative root 55 over 5. Like I said, I'm not going to round to the nearest hundredth on these. That's where I'm just going to finish this problem off. Okay, I have finished this review. I know that it took longer than I said it would and than I expected. A lot of the graphing took some time up and, some things happened, but I hope that I really clarified everything along the way. Good luck with everything. I really hope that this clarified some things for you. Fiend!